when sites are first starting with FortiFlow, I think a really key piece is to optimize the quality of imaging. But to do that, you do have to have software that you're ultimately going to be using for the analysis and viewing. But I can, I'm going to assume that the image quality will be relatively comparable to what I'm showing with this with our GD platform. We did just get a Siemens scanner recently, and are hoping to see the FortiFlow sequence on that soon. I'll walk through a couple things. Do you have do you see a fair number of congenital heart patients, or not so much?
Yes, we are doing congenital heart. We do both pediatric and adult.
Okay, both pediatric and adult. That's awesome. I kind of miss the kids. Let me see what I can find. Why don't I start with, so this is our newer queue of patients, so it doesn't have all of them, but I can walk through. How about that PAPVR case that I was just looking at? 1 second here. Yes, so this is one from, I don't know, a few weeks ago. Our standard protocol, since you might not have seen this, is a little bit different than how I trained, and what most people probably do. So I typically start with a 3-plane scout, a 3-plane localizer. Since we're imaging primarily at 3T, I do elect for a single shot fast spin echo instead of the typical SSFP because of the artifact of the SSFP. So this is kind of like a domino imaging where we're using a lot of single shot fast spin echo. But I realize that a lot of people like and are traditionalists and do expect to see Fiesta images or SSFP images. So this is what we typically see at 3T. A lot of off-resonance band artifact, for example, but it gives you a good survey, bright blood technique. There are no perfect answers here, but those are good. And then I'll move on to our a few planes, a long axis plane, a gated, and a optional horizontal long axis plane prescribed.
I don't think you're sharing yet. If you were.
Oh, sorry about that. That's foolish. Okay, here we go. So here we go. Just so you have a feel for it. Single shot, black blood, axial, black blood, and axial Fiesta or SSFP, and then a gated. So these are actually non-breathold, and then here's our first breathold. Here's a long axis in the horizontal plane. There's some flexibility for viewing here. I'll just increase my window size here so that you can see. It's a pretty good viewer now for most of our standard imaging. Then I'll do a short axis off of these long axis images. This is just a quick non-gated scout survey. That's basically 3 breath holds ahead of a couple other things. We started adding T2 mapping, and there's some functionality for that, and a timing bolus for contrast. And so you'll see that there. That contrast timing bolus gives us a way to prescribe a cardiac gated MRA. This is just a preview sequence here. The full cardiac gated MRA follows here. Let me see here. Which gives us some more detailed anatomy. That can be 3D reconstructed like a CT. I don't know if you also do a lot of cardiac CT there for function or congenital heart disease. So anyway, that's our typical protocol. Then, so that's maybe a couple breath holds. I'll typically also follow that with another acquisition. This is a should be a gated sequence, but this patient is probably an AFib or breathing during this particular acquisition. Then we'll have the 40 flow. So this is, let me just sort of use their screen space a little bit. The 40 flow acquisition runs for about, I'll typically run it for about 10 to 12 minutes. You can see the coverage is pretty large. This version of the 40 flow sequence that I use includes compressed sensing and parallel imaging in 2 directions. The parallel imaging in 2 directions, I don't drive to a very high level, but it's of acceleration, but it's typically roughly around an total acceleration factor of about 4, not super extreme. I've seen good results at up to 6 to 8, depends on the patient size. At very, very large patient sizes, which we see a fair number of patients, those acceleration factors cause the images to degrade quite a bit. Compressed sensing can bring some of that back, but not in very, very heavy patients. So those are some consequences of that are difficult to overcome anyway. But so this is a typical 40 flow case. For you guys, you probably see this as a common indication. This patient had a cath already and an echo, and they were not sure why they couldn't find the source of a shunt. So this is an obvious one where you have a right upper lobe PVR draining into the SVC. I'll typically do a couple different measurements. I know Misha, who's here on the line and helped remind me to share my screen, helped me write a paper a number of years ago where we brought together about 10 cases from each of 4 different institutions, and as a resident, he measured the QPQS using a number of different measurements, and I'll show you what those are like. So, for example, I can cut across the pulmonary valve. You might be used to doing that on the scanner, which we don't do anymore. But I know a lot of people still do. When's the last time you went to the scanner, Misha, for a congenital heart case?
For congenital, I cannot remember. Probably when I was a resident.
Probably when you were a resident, I know.
Which wasn't super long ago, but at least a couple of years.
Yeah, and I can't remember the last time I did too, but I cheat because I sometimes connect to the scanner remotely. So, but not to plan any specific planes anymore, like I would have in the past. This is basically how I do a pulmonary valve measurement, which Misha certainly, I'm sure, is familiar with. As you did this for that other case where you're looking for Epstein's or whatever. Or ASD, I don't know what that indication was. Okay, so that's our pulmonary valve measurement. And then we can do the same for the aortic valve to get a QPQS. Now, I noticed that there was some flow acceleration at the aortic valve. It doesn't look too bad. It looks like a bicuspid jet morphology here. But no, it's not. It's a normal trileaflet valve. In areas of flow acceleration, you can expect to see a little bit more artifact or inconsistency in the flow measurements, but I don't think this one will be so bad. I'll just measure at the aortic valve, or sorry, ascending aorta, but we can do another measurement at the aortic valve just to get a sort of upper and lower bound of flow measurements. So is everyone following what I'm doing? Yeah, pretty straightforward ascending aortic flow measurement here Now I'll also toggle off and on to the phase data. That's just hitting number 7. So, all right. So that's roughly it. Now, I think Michelle, you probably have talked to people about the sort of valve tracking type of thing that we want to do. I'll do one valve track.
Okay, yeah, that'll be good.
All right, so that's our typical measurement for QPQS. You know, you can see what my previous measurements look like at the aortic valve and pulmonary valve, and then what I did today. And then I also previously measured the right upper lobe PVR directly. You can see what the sort of error bar is on these flow measurements. And that's a really good and important thing to optimize when you're getting started with 40 flow, is not to try to over accelerate it so that your scan times are like 2 minutes or something, because while you can do that, in my opinion, the quantitative measurements are the reason why people come to get cardiac MRI for congenital heart disease. It's really the measurements of shunt volume, shunt fraction, regurgitant volume that people are getting those. So I don't mind spending 10 to 12 minutes early in my scan to get a really good 40 flow, and then I don't have to worry about looking at the rest of the scan because I've got all the information that I really need. So instead of spending only 2 minutes on something that's really important and spending 10 to 12 minutes on what's important and then sort of deferring the rest till later has been our strategy. So the other thing we can do is we can look to see where our previous flow measurements were. You can see I've done a measurement of the pulmonary vein as it comes in, as well as the 2 locations in the ascending aorta and aortic valve and near the pulmonary valve. We can do the same just to give you some idea of what the sort of options are. We can do the same at the right pulmonary artery here. So you can use that single click button to cut in a cross section across the vessel. But I'm already in plane, so, or you can just rotate however you like to get that plane that you want. So this is we can call this a right pulmonary artery measurement. And then we can see how well these things add up. In certain patients, it's definitely seen in TET and other things, asymmetric blood flow. And one of the papers that I never got around to resubmitting was a comparison of branch pulmonary artery flow measurements, the fraction that goes to the right lung and a fraction goes to the left lung, and how they correlate with nuclear scintigraphy, quantitative flow measurements, or perfusion from flow nuclear scintigraphy. So this is a decent RPA measurement here. That's pretty good. This sort of swirling that you see in the right pulmonary artery is something that I called the yin yang sign of the pulmonary arteries when I was a resident. I don't think it ever caught on. I wasn't important enough. So, but that was something that I noticed in very dilated pulmonary arteries. So here's a left pulmonary artery, the best I can do probably. And so you can see the number of options is practically infinite for how you might choose to measure. I don't typically do all of these unless there's a reason. Okay. Any questions about that? The other thing that you might notice is that with this, I'm only doing maybe 1 or 2 segmentations. I'm not spending a lot of time doing every single branch pulmonary artery, or every single phase of the cardiac cycle. So one of the things that I implemented when I wrote the software in the first time, excuse me, was to incorporate that interpolation aspect of things, so that in between the cardiac phases that you annotate, that you mark up, the software automatically fills in the phases in between. That was mostly out of sheer laziness. I didn't want to have to annotate every single cardiac phase to get a flow measurement. I was only a resident at the time of writing the software, so I didn't have a lot of time. I was, I just had to find a good ways, smart ways of doing this. So you can see there's a little bit of error between the branch PAs and the pulmonary valve. And that's a phenomenon we see quite a bit in very dilated vessels, like the ascending aorta after a bicuspid valve, or a very aneurysmal or dilated pulmonary arteries. You get a lot of vortical flow. So let me just illustrate what that looks like. If I bring in a right pulmonary artery seed, yeah, here we go. I'm going to hide some of these other things here. All right, so if I hide that RPA, oops, wrong one. I'll hide the, okay. So can you see this now? The flow in the branch pulmonary arteries, that so-called yin-yang thing, it swirls so much that basically we're not resolving it temporally or spatially adequately. So we can't expect the flow measurements to be accurate. You can see how complex this flow is. It's very dynamic, and we're probably not sampling it adequately. And it may be inconsistent from beat to beat. There may be a component of turbulence or whatever. So one of the papers that we wrote recently was a paper in radiology cardiothoracic imaging about vortical flow and how to quantify that. One strategy that we use to quantify that. When there is a tremendous amount of vortical flow, as you can see here, the flow measurements tend not to come out well. So an important aspect of quantitative cardiac MRI for this kind of thing is to know when you have many options of where to measure blood flow, what numbers to trust. And that was a key paper for us to get out there so people could understand this concept. Where you have more laminar flow, near the pulmonary valve, for example, you can trust that more. Where you have very vortical flow, the numbers tend to degrade quite a bit. And so when you have inconsistencies in your measurements, that can help you quite a bit. So that's a challenge for every kind of phase contrast, whether it's conventional 2D phase contrast or 4D flow. I think it might have been under-recognized for many years because we didn't have the ability to visualize flow this way. So there are two places that we could, in theory, measure flow here along this left pulmonary artery. We could have measured more distally or proximally instead of in the middle, where the flow is a little bit more laminar. So that it may be that if I redid the flow measurement in the distal RPA, I would get a higher number, a little bit more accurate number. The left side is also complicated here. So that's another reason to bring this up. And I'll just send those streamlines both forward and backwards. But it's maybe not as bad, actually. It's quite straight. So hopefully you're able to see that. This is just, you can see how vortical that RPA is at many phases of the cardiac cycle, right? So kind of complicated looking. Early in early systole, it's pretty laminar, but across the different cardiac phases, it gets really complicated. Okay, so hopefully that's clear. Valve tracking probably isn't super critical for this case, but I can walk through that as well. Let me see here. There's a little jet of tricuspid regurgitation. I could use that, even though it's probably not necessary. So let me do that. Okay, so just go here. This is the tricuspid regurgitant jet. Which you can see here. So I'll just start from here and do one segmentation of that. All right, something like that, 4 points. And then I'll scroll in time. You can move the position in any of these other planes of where where you want to measure that jet. And for no particular reason, I'll just move it here. And then when I move I don't know if you saw that, when I move the contour, it snaps that contour into the plane that I'm in. So I can measure blood flow across that regurgitant jet pretty easily, and then in a slightly different plane. And then as I scroll forward into diastolic phases, you can see the inflow. And so this is probably the last phase that we have regurgitation. Maybe there's a little bit more after this. It's sort of temporally averaging the regurgitant jet with the diastolic inflow. I'm just going to shrink this segmentation to 0. So there's probably very little flow there. Just walk over to early systole and maybe move forward a little bit more. Here we go. So I see the jet again. Maybe I want to move a touch back. So, and then my orientation is not quite right. So it's not just a position, but my orientation to follow that regurgitant jet may need to change. So that might be good. So this is what I believe our regurgitant jet looks like in this phase. Something like that. I think that's true to the regurgitant jet at the early part of systole. Yeah, you can see on this plane how broad it is at the very beginning of systole. If I move back one frame, and there's still a little bit here, so I'll just segment this. The tricuspid is considerably easier than the mitral because the jets are almost always straight. They may move a little bit, but they don't usually move a lot. So that's part of the reason why I suggest first looking at the tricuspid if you're going to use, if it's important to quantify with cardiac MRI, which it usually is. In a lot of these cases, you can kind of guess what the severity of regurgitation will be. If I don't like a phase, I can also delete it. And when I delete the entire segmentation, it'll revert it back to interpolating in between phases. So if you, like I just did, I took off one of the segmentations and I can redo it pretty easily. So that's those two phases, and then we'll just quickly walk through this. Now my orientation is a little bit off. So when you guys are doing 2D phase contrast, Kathy, do you guys do multiple cuts through the valve, or how do you, what is your typical strategy? Oops, I think you're muted.
Yeah, the valve has been, I mean, aorta and pulmonary, we usually get at least 2. Mm-hmm. And mitral and tricuspid, especially mitral, we do that subtraction. But the direct measurements has been challenging, and it's very inconsistent value.
Yeah. Yeah, a lot of people do the indirect approach instead. taking the stroke volume and subtracting off the net flow or from the valve, from the outflow valve as a good strategy. Yeah, I think even that is complicated because you can have error in your stroke volume measurements from your standard anatomic short axis SSFP or whatever. But this is pretty typical. So this we're getting about 1 liter a minute of tricuspid regurgitation, and our pulmonary outflow is about 8 roughly. So 1 out of 9 is about 11%. So that's mild regurgitation, which is basically how it looks. The nice thing about FortiFlow, unlike echo, is that it's not directionally dependent. So we can set our color scale a certain way. I typically use 150, and that visual assessment is pretty good and pretty consistent. There's been a couple different papers on visual assessment with FortiFlow, and it seems to correlate quite well with the quantitative numbers. Now you're going to see a couple things here. In this particular case, you know, when you look at the pulmonary valve flow, oops, not that, that's too extreme. You'll notice that there's about twice as much volume coming out of the pulmonary valve, and you can visually get a feel for that compared to the aortic valve. The aortic valve is this big, and the pulmonary valve is this big, right? It's a lot bigger. About twice as much volume is coming through it. You can guess that the QPQ has this too. So I would imagine that if someone wanted to have a couple different radiologists look at the flow, they could probably predict the shunt fraction just by looking at it. I've never done it systematically, but that's certainly a possibility. So you've seen now how I do tricuspid regurgitation. I did something similar for the PVR up in the right upper lobe. And one of the reasons to do that is just to reassure yourself you're not missing another shunt somewhere. If it adds up well, you have the PVR directly measured, and that is the difference between the pulmonary valve and the aortic valve, then you know you're quite confident that you've caught everything. The other thing that comes up, especially in a case like this, is whether or not there's an atrial septal defect. And one of the really great things that I really, in that earlier paper with Misha, actually, we figured out that there are a couple really great planes to interrogate. And one of them is a sort of a natural interrogation of the atrial septum with the IVC flow. If you see it, you can see that there's, if you look here, you can see that there's a stream of blood that naturally hits the atrial septum. And that stream of blood is basically consistently interrogating that septum for small ASDs or PFOs. That's how this is designed, I suppose. You can see there's not a big shunt here. Most of the flow you're seeing coming in is coming from these pulmonary veins in the back. So I'm just sweeping through and looking at the atrial septum in this way. So I don't see anything actually, nothing that convinces me that there's a atrial septal defect or PFO of any sort in this patient. So you can increase your sensitivity for detecting small shunts like that. You can rotate it a little bit more on axis of that atrial septum. Whoops, here we go. There you go. So you can convince yourself that there's not a ASD or PFO. I really like this view a lot. I don't know if I've ever written anything on that, but hopefully people will like that. Then you can also,
very nice.
yeah, it's really great physiology, huh?
Yeah. And do you have similar trick for a VSD?
Yeah, I'll sweep both in short axis and long axis. Like here, I'm sweeping in long axis. And we try to do that also with conventional MRI. I know a lot of people do both an axial stack and a short axis stack to sort of get that same look. But the problem is SSFP is not flow sensitive. So you always wonder if you're missing it because you can't really see the flow. You can only see the septum, and the septum is going to be really thin. So I really struggle with that with conventional imaging. Same thing with ventricular septal defects, but it's not as pretty with a jet. But you do have a pressure gradient between the LV and the RV, which will be a natural interrogation as well. You don't see arrows bouncing off the septum quite as much, but you will see if there is a jet, it'll be a high velocity jet. It won't be a little blue jet, it'll be a red jet because the gradient between the LV and RV is pretty high. So if you back calculate what that is, a gradient, so the LV pressure may be what, systolic at 120, right? And the RV, even with pulmonary hypertension, 50, right? So a gradient of at least 70 is what you're going to be expecting. So there's going to be high velocity of flow across it. What is modified Bernoulli? So let me try to bring up my calculator here. So if we say a gradient of 70 divided by 4, and then take the square root of that, that's going to be 4 meters per second. So that will easily be red. So if there's a VSD, you're going to see a red jet, no question, for pretty much everyone. All right, that's a lot of time spent on a PVR, but I think I showed some valve tracking, some sort of dynamic interrogation of the atrial septum in short axis, long axis, and some flow measurements. What else can I show you guys?
This is a very basic question, but when you were drawing the circle to measure the velocity for the flow, the circle was a little bit more generous than regular phase contrast. Is that right? What would you recommend?
You mean how to draw the segmentations? Yeah. So a number of years ago, people published on that specifically. I remember seeing some paper from 30 years ago from Norbert Pelk, even where they drew big contours, because most of the velocities outside of the vessel, as long as you're not drawing a contour into the other vessel, are zero, right? Because they're unless you're in noise, right? So there's a couple things in the lungs. There's a lot of noise. There's high velocity positives and negatives. I don't worry too much about that. In general, on average, they average 0. But if I was more careful, I would also exclude those as well. But the key things to avoid are really to avoid segmentation of the adjacent vascular structures. Fortunately, in this case, it's orthogonal. So the component of flow in the parallel with this vessel is small. Parallel with this, the normal vector of this plane is small. So it's not going to contribute a huge amount to flow measurements. You can see what happens if I do that, though. It will drop my flow measurement from 3.8. If I'm doing a poor job at segmentation, it can affect the quality of my flow measurement, right? But it's not tremendous, it's a little bit. I tend to, and I teach the other faculty and trainees to segment slightly generously and use the basically the phase data to guide you, as well as looking at the anatomic images, right? I don't segment just the forward jet because that would not be hemodynamically accurate or fluid mechanically accurate. So anyway, that's hopefully that's clear. I segment a little bit big, but yeah, you can see the amount of error that introduces when you're a little bit off or a lot off.
Albert, can you just quickly going back to the tricuspid regurg segmentation that you did? Can you just hit on the interpretation of the data here in our software? Because this jet is entirely regurg, but the numbers show up as forward flow.
Oh yeah, I mean, yes. Yeah, I think you just have to know what you're measuring. In this case, what I'm measuring is the jet itself. So this is forward with respect to the plane, not forward with respect to the circuit of the heart and the vessels. So when I segment it, you know, I'm looking at the amount of flow that goes backwards in this plane because I'm segmenting the jet itself. And this is a pretty decent waveform, and it's consistent with what you saw visually. The first two phases of the cardiac cycle, the tricuspid jet was pretty big and generous, but then quickly it became small as the leaflets coapted, and then the rest was a diastolic phase. And there's two sets of, you know, I kind of gloss over this really quickly, but there's a measurement of the flow in liters per minute, but you can toggle it to flow in milliliters per beat. I know a lot of people are comfortable with that as well. These are great because there are some good echo guidelines for severity grading that are complementary to the regurgitant fraction. So for regurgitant fraction, we have a good paper I think that was in JMRI 2015 or something like that, that one of my former residents wrote, who's also a faculty at the VA, Jen Fennis, and she did direct and indirect measurements of mitral and tricuspid regurgitation, and we have the equations there that people can follow. Ideally, it would be great if Arduous implemented those calculators into the software at some point, where we could input which one is a regurgitant jet, which ones are forward jets, and eventually work towards automating some of those measurements. But good guidelines for echo are the thresholds are like 30 and 60, which I think a lot of people think are a little bit high thresholds for moderate and severe mitral regurgitation. In practice, I think where we see, in more recent literature, we see the upper limit for or lower limit for severe to be around 50 mils per beat, around there if you look at the literature, and maybe 25 for moderate, as sort of a way of bisecting the 50 and 0. This is well below that. So when I report mitral and tricuspid regurgitation, I will report both. I'll report regurgitant fraction as a percentage of the forward flow, and so in this case 11%, as well as regurgitant volume of 15 mils, which is well below 25. So I know it's mild. So that's nice as a way of, you know, sort of checking yourself that all your interpretations are consistent. Does that make sense? Okay. Why don't I show one other thing? We just did this iron study recently on upgraded version of our 1.5T. So our 1.5T in our main hospital is, what is it now, like 20 years old? And we just got it lifted in one day, which is pretty freaking awesome. Like this is what the images look like from our standard SSFP. You can see there's a lot less artifact. The band artifact is pushed off the outside a lot, and then our standard SSFP images are a lot brighter than at 3T that you just saw. So this is just our standard non-contrast iron protocol, and we have just basically function for these patients. But I was really pleased by the image quality. that we're now getting pretty routinely on this scanner, which is 20 years old, but it looks like a brand new scanner. It's pretty freaking cool. Yeah, anyway. For T2 mapping, or T2 star mapping rather, in this case, I'll just bring, I already have the workflows up, so I can just bring those in. I'll usually do a septal measurement. I did this lateral measurement to illustrate to a fellow why not to do a lateral measurement, because of the dephasing at the wall, because he was wondering why I measured only the septum. You know, basic functionality. Hello, am I doing this wrong? Oh, here it is. Doing the wrong thing. You can see, well, that's pretty cool. The curves fitted for both the blue contour and the green contour. At the lateral wall, you have the effect of magnetic field inhomogeneity related to the lungs. So that's going to naturally drive your T2 star values lower. We don't need to do a paper on that. That one is free from just basic first principles of physics of MRI. So that is a normal T2 star. Let me see if we can see where the numbers are. Oh, they're here. 49 and 31. They're both normal, but anyway. And then in short axis, we have our T2 stars as well. Oops, wrong one. It should be this one maybe. Ah, yes. So I did that on the septum, and then I can add another contour for the liver. So there's basically a borderline of mild to moderate iron deposition in the liver, below 20 millisecond, but in the heart it's normal. Is that how you, are those the thresholds that you typically use for iron, Kathy? 10, 20, 5, something like that?
Yeah, that's what I use. Mm-hmm.
Yeah, so I think that a lot of people are pretty much consistent on that. For 1.5 T, and I don't have any of my patients at 3 T, although you could, I think the numbers are half roughly, but we typically just send them to the 1.5. Okay, does that, oh, I guess for cardiac function for this, a lot of companies now have that kind of, basically the AI type of segmentations. So I don't spend a lot of time doing these. I usually have, I usually read a couple of these out on my own without a fellow because it's faster. Just kidding, I like my fellows. But that wasn't the case before. I would, you know, I think when I was a trainee, I read every single case, and my attending would not read any cases by themselves because that would be too much work. But I read a fair number of cardiacs on my own, just because otherwise I'd be there all day. Anything else, guys, that you have an interest in, I can try to bring up? Oops, you're muted, sorry. I think you're muted still, Kathy.
All that post-process information, is there, how do you transfer to PowerScribe on the report?
Oh, good question. That one's a softball. I like that. That is actually one of the, I don't know, one of the holy grails that we've been trying to get done for years and years, as not Arteris itself, but in general. That how do we not dictate numbers? These ejection fraction measurements, all that stuff, stroke volume, are tabulated into the Arteris system. But I basically just hit this button, publish for fluency, at the top right on the report button. And there's a similar button for PowerScribe if you use PowerScribe. And that will populate into a token automatically on your report. So I have that enabled in my system. There's also a button to sort of make it easier to launch the software. So on my PACS system, I have a button that says Arteris on it. I launch it, kind of like you can do with TerraRecon and all these other third-party softwares. There's a way to do PACS integration, I basically do that. So I can launch Arteris and I can push the images back into our system that way. And so that's something that I wish other vendors, all the other vendors of all other software would do as well, because we spend an inordinate amount of time making mistakes dictating numbers. But anyway, so now we don't have to do that. There's other ways also to issue reports. There's this button, publish report. So these numbers, T2 star values, everything can also come in as a DICOM capture of a PDF. I think I should be able to download it. Oh, maybe not. For some reason, I don't have the download button, Michelle, on this particular. There's only a publish button, strangely.
Are you logged in through your network, like through your hospital network?
Oh, that might be why. Yeah.
Yeah, it won't let you download if you're not
Right.
logged into your network.
Yeah, you'll notice that all the exams are de-identified. So these are clinical exams, but they're de-identified even if you have access to the software, unless you're connected to the VPN to access the PHI, because the PHI is stored on premises, at least at our institution. So I guess there's some functionality that's disabled when I'm not connected to that VPN. The other thing that you can do is you can make these video captures, there's some nice functionality there where you can you can push these also to your PAC system. You just publish the video and that'll go up to your PAC system, or you can download them like I did in this case. I'll share this Windows Media Player. This is just playing on my computer now. So that's pretty handy for publishing for a number of different reasons. I can also do the same for the cardiac function as well. Let me see if I can find that. Here it is. Download video. Here it is. So here's the cardiac function video. So you can send that as evidence that you did your cardiac function measurements. Now, obviously, I didn't segment every cardiac phase. I only did the end diastolic and then systolic. The rest has really been, well, I edited those two, but the rest are just the AI's initial guess for this case. When the image quality is this good, the AI does really, really well. When it's even at 3T, it does decently, but these are very clear. So, all right.
AI that you're talking about for calculation of LV function and RV function, is that available on current software, or is that just research?
Oh yeah, no, that's part of product. That's been product for like 3 years now. I think Arteris made that. What is it? When was FDA clearance? Like December of 2016.
It's been 3 or 4 years.
Yeah. The one criticism that I have of the company, the biggest criticism, is that there's not enough marketing that people realize that those things are actually been product for a long time. But that's because we just don't have enough people there to let people know about that. The product itself is pretty awesome, I have to say.
It is very impressive, and thank you. I learned a lot.
Is there anything else, guys? Michelle, Misha, that you guys wanted to look at other than what I have already seen? I think we have a few more minutes.
No, that covered it for me. Thank you. I appreciate it.
Mm-hmm.
Yeah, that was great. Thanks, Albert. Always good to be with you. I got to actually run to my meeting with Seth anyway. So.
Oh yeah. Okay. Good.
Take my lashings.
Take your lashings. Yeah, I have mine later today too. Fortunately, that they're all virtual now. Virtual lashings.
Exactly. Thank you, though. Appreciate it.